Hello, Mr. Simon. Today I will solve a problem and show you the steps, and I will explain the solution. I will try to solve this problem and explain. So, we have a function f x y equals x to the power 4 plus y to the power 2, which we want to find the extrema of the subject to the constant gxy equals x to the power 2 plus the y to the power 2 minus 1 and equals to 0. So we introduce a new variable lambda, the lambda sign, which is the Lagrange multiplier, and consider the Lagrange function. So L x y lambda sign equals f x y minus lambda g x y. This function incorporates both the original function and the constraint. So we need to calculate the partial derivatives of the L with respect to the x, y and lambda. So these derivatives will be set to 0 to find where the function doesn't change. So which are our potential extrema? So let's try it. L x equals partial derivative of x and x to the power 4 plus y squared minus lambda and we shouldn't use bracket and x to the power 2 minus 1. So the same thing for the y. So it will be the same thing like this. L y a y. So everything will be same as this. So for the lambda also this will be the same thing. So we solve the system of equation given by this partial derivative. So I just wrote the one of them. So for y and for lambda are same. So this is the same for all of them. So these partial derivatives to set to 0, and so let me erase this part. So we solve the system of equation given by these partial derivatives set to be 0. So let's go ahead and find these derivatives and solve the equation. So L x equals, so we're finding the derivative of this and derivative of this is the also same for it. So let's find for x, derivative for x. So we have a lambda here, so it will be negative 2 lambda x plus 4 comes to here, so it will be 4x and minus 1 4x cubic. So this is the partial derivative of x1. So let me erase this part. Okay, the L for y, L y equals, okay, the same thing like the Ly, the lambda y, and plus what was our equation? It was like 2y. So L lambda, now we find it for lambda, so it will be like this: x squared minus y squared plus 1. So I erased the equation, but I remember, so that's why I wrote it. So this is the derivative of the Lagrange function with respect to the Lagrange multiplier and multiplier lambda. So which essentially just gives us back to the constraint x squared plus y squared equal 1. So with these derivatives in hand, we need to solve the system of equation where each of these derivatives is set to the 0. So we will equal all of them to the 0 and for it also 0. So to find the values of x, y, lambda, so that satisfies this equation. So we solve this equation. We solve this system. So like this. It will be like in one system. So this, and this equation in this system. Okay. So this will give us the critical points that could potentially be maxima or minima for our original function f xy. So under given constraint, let's proceed with the solving the system. We have solved the system of equation arising from the partial derivative set to the 0. This solution gives us the critical points where the function f xy x to the power 4, which was our first function, plus the y squared could have extrema to be constrained x squared plus y squared equals 1. Here are the critical points. So let's write the critical points. So x, y, lambda. The first critical point 0, -1, 1. The second one, lambda equals 1, 0, 1, and 1. X, y, lambda equals negative to the root square divided by 2 and negative square 2. So I wrote them ready and equals 1. So that's why I wrote fast, so not losing time. So that's why these are ready. Negative square root 2 divided by 2, square root 2 divided by 2 equals 1. And this is the fourth one. This is first one, second one, third one, fourth one, and the fifth one. X, y, lambda equals square root 2 negative 2 divided to 1. So 6 1. X, y, lambda equals to the power 2 divided by 2 square root 2 divided by 2 be 1. So 7 x, y, lambda. Negative 1, 0, 2. And the eighth one, x, y, lambda equals 1, 0, 2. So each of these points satisfies to constrain the x squared plus y squared equals to 1. So the next step will be to plug this x and y values back into the original function, which is the fxy. So determine the corresponding function values, which will tell us whether each point is a maxima, a minima, or a saddle point. So for this, let me write this. Let me take another marker. Okay, so so at at xy, which point 0 and negative 1, the function f 0 and negative 1 equals 1. So for this it will be 1, negative 2, 2, 2, 2 equals 1. Wait a minute, not 1. It equals 3 over 4. So I will write this part very fast because it takes too much time. So that's why I will. So f So given these values, the points where the function value is 3 over 4 are the minimum of the function under the given constraint. So because they are the lowest value obtained values, so the points where the function value is 1 are not the minima, since there are other points with the lower function values. However, without the further analysis, we can conclusively determine if there are maxima or saddle points, since we are dealing with constrained optimization problem. So if there are a maxima or a saddle points, since we are dealing with a constrained optimization problem, the usual second derivative test doesn't directly apply. We will need to perform addition analysis to classify these points definitively. So thank you everyone. I tried to explain it detailed. Thank you. See you later.